Good day everyone. Today we are presenting our project on predicting student dropout in universities. Let's start by addressing a major issue in higher education, the high rate of student dropouts. Many students leave university before completing their degrees. This creates significant challenge not only for the students who face difficulties in securing good job opportunities, financial struggles and miss career goals, but also for the universities themselves, which suffer from lower reputation, reduced funding and negative academic performance. So how can we help prevent this? The key is early identification. Universities can take preventive action if they recognize warning signs like poor grades, financial challenge, or lack of engagement. This could lead to interventions such as additional tutoring, financial support, career counseling, or mental health services, ultimately reducing dropout rates and ensuring more students graduate successfully. In our project, we have analyzed student data to find patterns that indicate a higher chance of dropout. By examining various factors such as academic performance, family background, and economic condition, we aim to predict which student may struggle to complete their degrees. Our prediction could then help universities intervene early and support students in need improving graduation rate. Our objective for this project are as follows: to analyze student data and identify key factors contributing to dropout, apply to machine learning model to make predictions, to compare the performance of these models using metrics like accuracy, precision, recall, and F1 score. Finally, we aim to optimize the model through hyperparameter tuning to improve prediction accuracy.
Dataset overview. This project uses a dataset about students from different undergraduate programs like agronomy, design, nursing, journalism, and management. The dataset got from Kaggle, and the data was collected when students enrolled. The includes important details about their academic choices, personal background, financial situation, and first year performance. Main features of the dataset: academic program shows the students' study program. Demographic includes details like age and gender. Financial situation includes family income and financial support. Academic performance shows students' grades from the first 2 semesters. Class imbalance: most students either graduate or stay enrolled. Target outcomes: each student falls into one of these three categories: graduate, completed the program successfully; dropout, left before completing the program; enrolled, still studying in the program. The goal is to use machine learning to predict whether a student will graduate, drop out, or stay enrolled. Why this data is useful for universities: finding at risk students helps identify students who might drop out so universities can provide support. Improving graduate rates helps universities understand why students drop out and find ways to help them stay. Better resource allocation helps direct support like financial aid or tutoring. Challenges with the dataset: class imbalance. Since fewer students drop out, missing data. Some student details might be missing. So we need to handle this to make better predictions.
Let's go through the steps we took to explore and prepare the data. First, we loaded the dataset and checked its structure. This helps us understand the data and find any problem, like missing values or unnecessary features. Next, we looked at the target variable, which how many students will into each category: graduate, dropout, or enroll. We noticed that there are fewer students in the dropped category, creating an imbalance that we need to handle when training our model. For categorical data, we used two encoding methods. The first one is label encoding. For categorize with only two options like gender or marital status, we convert them to 0 second and 1 second that machine learning models can use them. Another one is one hot encoding. For categorized with more than two options like mother, occupation or course, we created separate column for each category, making it easier for the model to understand. To avoid a problem called multinationality, we used drop first equal true option. This removes one category from each set to prevent redundancy and improve the model performance. Then we scale the numerical data because some features had different ranges. We used standard scaler which adjusts the all values have a mean of 0 and standard deviation of 1. This prevents large numbers from influencing model too much. Finally, we split the data to training the testing sets using trade test split. We used 18% of the data and training a 20% for testing. Ensuring the good balance, we also set random state equal 42 so that split the remains the same every time we run the code. Now I will hand over the Sampath who will discuss model training evaluation.
Today, I'll summarize our model implementation and hyperparameters tuning effort to enhance performance with three machine learning models: logistic regression, random forest, and support vectors machine. We started with logistic regression, a common choice for binary classification. We adapt it for our multi-classes problem using a one-piece rest strategy. While efficient, it can struggle with complex pattern, achieving an accuracy of 75.9%. Next, we implemented the random forest classifier, an assemble method that combines multiple decision trees to improve accuracy. It effectively reduces overfitting and works well with high variance datasets, resulting in an accuracy of 76.7%. Lastly, we used support vectors machine, which excels in high dimensional space and non-linearly separatable data, achieving an accuracy of 76.9%. To enhance the random forest model, we performed hyperparameters tuning using grid search with grid search CV from skitchlearn. By optimizing parameters like the number of the estimator and max depth, we improve its reliability and predicting student dropout.
So let's move to the demo. So let's begin by loading the dataset and inspecting it. We will check the first few rows in the data types. So let's run this one. So you can see the first few rows and data types. Next, we will visualize the target variable distribution with a pie chart. Yes, you can see that. So before we move on to the feature engineering, we need to make sure that there are no missing values in the datasets. So let's run this one. So you can see there are no missing values in this dataset. Next, we will handle the categorical variable. So let's run this. So after encoding, the categorical columns are now represented as numeric values, which machine learning algorithms can understand and work with. And then feature scaling is an important step to ensure that all numerical features are on the same code. So let's run this one. So by scaling the features, we are ensuring that the machine learning model treats all the features equally, which can improve its performance. And then now we need to split the data set into the training and testing sets. So let's run this one. So, okay. So let's start by training a simple model, logistic regression. This is a popular model. So let's run this one. So as you can see, we get a classification report. So in here, you can see our accuracy is 0.759. So it's a good one. And next, we will train a more complex model, random forest. So let's run this one also. And also we get a classification report. In here, you can see our accuracy is a little bit increased, 0.767. It's a good one. And so now we are going to train the support vector machine model with a linear kernel, the SVM. So let's run this one. So you can see the classification report in here. So we have more accuracy 0.7694. So it's a more accuracy one. Okay. So finally, we will improve the random forest model by tuning its hyperparameters using GERD search. So hyperparameter tuning helps us to find the best parameters for the model, improving its accuracy and performance. So let's run this one. So, okay, so we have found the best hyperparameters for the random forest model. So thank you very much.